So in this chapter, we're going to look at invertibility properties of linear maps. And so we'll start off with this clip, which is just about actually invertibility of functions. So just like you remember from set theory or your theory of proofs class, there's nothing in here, especially in this particular clip, that's especially pertinent for linear maps. We'll get to that in the next clip. So if we've got a function from a set x to a set y, it's said to be invertible if there exists an inverse. So more precisely, if and only if there exists a g that has domain y and codomain x, so going in the opposite direction, such that if you compose the functions one way, so g of f, that gets you the identity function on x, and if you compose them the other way, so first do g and then f, then that gets you the identity function on y. And then in this case, we say that g is the inverse of f, and we write it as f to the minus 1 power. Okay, and so the first proposition that we have about inverses is that they are unique. So it makes sense to talk about the inverse. And the proof is real straightforward. It's the standard, well, let's suppose we've got two, and then, oh gosh, oh my golly, surprise, they're actually the same. So suppose that f from x to y is invertible, and that g1 and g2 are inverses of f. And so by that, I just mean that they satisfy these composition properties. If you compose them on either side with f, you get the appropriate identity. Okay. Then let's see. For any element of y, so I want to show that g1 and g2 are the same. And g1 and g2 are both defined on y. They map y to x. So I'm going to show that they do the same thing to any point of the domain, and then that'll show that they're the same function. So I say g1 of y, so that is g1 of, and then I can always sneak in composition with the identity because the identity by definition doesn't do anything. And then I'm going to expand that one as f of g2, right? Because g2 is an identity. And applied to y. And then if I look at that, what have I done? I've done g2 of y followed by f applied to the result, and then I'm applying g1 to that whole thing at the end. So that's the same thing as g1 of f of g2 all applied to the function y. And then let's see, so now this is the same thing as applying g1 of f after applying g2 to y. So I can apply g2 to y, and then I'm gonna do g1 of f applied to the result. And so this is basically, I'm using associativity of composition here. And so then if I look at g1 of f and I evaluate that, since g1 is an identity, that gives me the identity on x applied to g2 of y. But when I apply the identity to something, nothing changes. So that's just g2 of y. And now reading from beginning to end, you can see that g1 is equal to g2 on any y. Okay. There's one other general result that's true for function, any kind of function, not necessarily linear. And so this is called Prop 356 in the book. And actually, let me give myself a little more space there and pull it down. Okay. and it is that f is invertible if and only if f is both injective and surjective. And so there's a term for this right here. So if something is injective and surjective together, it's called bijective. And so if there's a bijective correspondence between two sets, it means that you can pair off the elements of those two sets exactly with no duplications and nobody left out. I'm not going to go through the proof, but I will give you sort of the idea. The idea that f is injective. This corresponds to the property of f inverse satisfying the vertical line test. So in other words, if f is not injective, there's no way to define f inverse, a function f inverse that satisfies the vertical line test. And similarly, f being surjective, that's the property of f that allows for an inverse to be defined on all points. Okay, and so like I said, I'm going to skip the proof. So we'll move on to the next clip where we'll start discussing linear maps.